Hi, now we will look into chapter 6, Earth Observations, Technology and Solar Systems. So in this chapter, basically I will talk about the remote sensing technology, where it will be one of the primary sources for you to do the mapping, apart from the GPS data that you collect on the ground, and also the maps that you trying to get from those various agencies, either in hard copy or soft copy. So please bear in mind that even though this is not exactly a GIS, it's remote sensing, but the importance of this remote sensing is basically is a main data provider for the GIS analysis. Okay. Okay, the first one we look into the settings or the properties of the satellite data. And the famous satellite data that we use for the environment monitoring is the multispectral data. Okay, in multispectral data we have these different kinds of informations, which is we call it as bands, and these spectral bands is all about the layers of the informations of the remote sensing data, and it can be separated into several types of bands. And the first one will be the coastal, blue, green, red, yellow, which this will form this what we call it the actual photo, or the natural the real photo of the informations of the Earth's surface. Okay, and for the NDVI, NDVI means normal differential vegetation indices, near infrared, short wave infrared, and thermal infrared is those informations are not seen by our naked eyes, but it carries a lot of information, especially for the environment monitoring, such as for the chlorophyll, water content, for the minerals, and many more. Okay, so basically the satellites of remote sensing satellites such as Landsat, IKONOS, QuickBird, they will collect informations, and the informations they get is basically the reflections of the wavelength from the sun as a main source of energy to the target, which is the surface, and will goes and reflect back to the satellites, and so we record it. And those graph actually tells you the pattern of the reflections of different kinds of the spectral bands. Okay, so in satellite images, okay, we have these panchromatic images, which is black and white. You can see this kind of this kind of data in our Landsat satellites and Worldview 2 satellites. It shows you the black and white informations, but with detailed physical patterns and more. Okay, for the multispectral image, it consists of the several bands of data, and each band basically for the yellow, green, blue, those things, it displays as a grayscale images, and if it's combined using the software, it will produce the color composite image. Okay, and those spectral reflectance is utilized to interpret what kind of features being recorded by the system. And this color composite image is basically a combinations of the three primary colors, which is red, green, and blue, used to display composite image. And this RGB is basically, you might heard this because the digital camera uses the same concept for the combination of RGB and displayed to our computer monitor, and it will produce RGB's combinations will produce 16 million different kinds of colors spectrum and so on. Okay, and we have this true color image. It resembles closely what being observed by our human eyes. This is what you always see in our Google Map or Google Earth. False color combination is being used to identify certain objects where we intentionally put the infrared images, okay, on the red channel of the display of the monitor, so that it can highlight the informations that being recorded with the high reflections of the infrared. And of course, there are natural colors, okay, for image that lacks one of the more three primary visible colors. Some of the satellites, such as spot, they doesn't have any what we call it, any blue color. Therefore, we will what we call it, we will trying to manipulate the available colors in order to resembles the actual color of the environment. And we have this normalized difference vegetation index, NDVI. So different bands can be combined to accentuate vegetated areas. Okay, using this, it can give you the areas that have the high ratio of the chlorophyll, and thus will give you the idea of the status of the plant health. Okay. So first we will look into the available satellites which you can use for the analysis. Okay, so the first one will be the Landsat platform. Okay, it is the oldest land surface data systems, and now we have the Landsat 8. Okay, these are the Landsat properties from 1 to 3. The spatial here means the 1 pixel resembles only 79 meter, represents 79 meters on the ground, and they have 4 bands, and the temporal is about every twice a month, and the geometric will be the scale of the sensitivity of the computers to record the reflections from 6 bits to 8 bits. And we have the Landsat 4 and 5. It has 7 bands here. Okay, and still it orbit the Earth twice a month. However, the geometry is about 8 bits. Okay, and these are the bands available. We have the blue, green, and red, near infrared, mid infrared, thermal infrared, and medium infrared. So there's a more information can be identified here. You can look into the near infrared to observe the chlorophyll index, the plant health, and so on. Middle infrared to look into the water content and so on. Then thermal to look into the temperature of the surface. Okay, so here you can see what are the usage of those bands. Okay, by looking on this, you can understand that you can look into the different informations from those bands, and you can estimate the reflectance, and can relate it with the occurrence of those elements in the environment that been recorded. And we have the Landsat 7. They have is 8 bands. Okay, and it has 30 meters and 50 meters. It's quite good. So the band 8 is the panchromatic. Okay, however, for the thermal is about 60 meter by 6 meter. For every pixel, it can give you quite good data for you if you want to come up with the urban heat island analysis. Now is the latest one. This is Landsat 8, much better. We have 11 bands to be utilized. Okay, it's a lot actually. Okay, thermal infrared, they have 2. One is for the surface, one is for the atmospheric thermal. So you can estimate those two. You have this 2 shortwave infrared, you have a near infrared, and you also have the coastal bands for the water, for the coastal monitoring. Okay, these are examples of the band combination 2, 3, and 4 RGB. Okay, and other one Okay, we also have the Spot platform. So Spot basically is from the Europe. Okay, it's a paid one. However, for Lancet, it's a free one. Okay, so Spot give you much better image where the spatial resolution is higher, which is 2.5 meter. Okay, and they have the TERRA. It's very good for you to observe the climate, weather, and also the ozone layer. Okay, and we have the Aster as well. Okay, Modis here. Okay, if you have any questions, you can try to Google around, or you can ask me directly. Okay, and these are the users of the bands for the Modis. However, the spatial resolution is very low, which is about 450 meter per pixel until 1 kilometer per pixel. Okay. And IKONOS is very good one. It's a commercial satellite. You can buy it, but it's quite expensive. Okay, QuickBird as well, and Worldview 2, in GeoEye, okay, COMPOSITE, LIDARs, and last time we do have we tried to launch our own satellite. However, it was a failure. Okay, and of course we do have the Hyperspectral. Okay, so Hyperspectral is basically a huge numbers of the continuous bands, where it provides a complete record of spectral responses of materials over the wavelength considered. And this hyperspectral data can be analyzed in much more advanced ways because of the detail of the bands. Okay, and have many narrow bands. Okay, where it can resolve the individual mineral absorptions. It can also determine the species of the trees. Okay, mostly used for geology or vegetation studies, and usually most of it are using the airborne system. Okay, so basically for the hyperspectral versus the multispectral is about one photos or one scene of the imagery will have about 5 to 7 files, which for every different bands. But for hyperspectral, if the system can record for 400 bands, therefore it has 400 files for one area of study. Okay, but the signal will be different. As you see here, it has a more subtle and detailed reflections across the wavelength. However, for the multispectral, it only give you reflections, the data on the specific band region only. Therefore, it gives you detail on the characteristics of the reflection. Thus, it can provide you with the signature of the reflectance as opposed to the multispectral. So the difference between the multispectral and hyperspectral, so multispectral, they separate the spectral gaps, the bands. However, multispectral, there are no gaps. Multispectral, they have the wider bandwidth. Therefore, those range will be average, become the average numbers of reflectance. However, for hyperspectral, there are no such thing. They are narrow bandwidths. Therefore, for every bandwidth, there are absolute numbers of reflectance. For multispectral, it's a cross representation of the spectral signature. However, for hyperspectral, it's a complete representation of the spectral signature. Multispectral, smaller image size, but remember that for Landsat at one area is about 1 gigabyte, is still considered small. Hyperspectral, large image size, ability to detect subtle spectral features, and in order for you to do the calibration are time consuming. Okay, so spectral resolutions. Okay, high spectral resolution is the key to the expression of the subtle material differences, where multispectral can only distinguish between different significant materials, such as example rod or vegetation, but hyperspectral can go up to the intra-species variation. So high spatial resolution is a key for the mapping of details, scale-dependent variations, as hyperspectral data is normally being acquired from the airborne. Okay, it permits the acquisition of the data with very high spatial resolution with a very high spectral resolution. Okay, so how does it goes? Have to fly first with the onboard the system, and after that we're using the software to do the processing, and we use the mobile spectral radiometer to do the ground verification, and after that we come out with the maps. Alright, we talk about the data acquisitions. We of course we are using the airborne, however there are also some field measurement or using the lab measurement in order to do some calibrations with the airborne data. So field spectrometer, we are using the spectral radiometer, go to the field and record the signature and compare with the images that we collect from the airborne, or we can bring the samples back to the lab and put it inside the spectral radiometer in the lab. Okay, and these are the types of the platform of the hyperspectral. Hyperion is the satellite based system, however for others, Aviris, Kasi, Chris, HiMap, ISA is a airborne system. Okay, and what are the applications of hyperspectral? It's good for forestry, environment, agriculture, transport and utilities, urban, as well as the military and defense. Okay, so in forestry, what can do? Species identification or stress level of trees in detail. For environment, oil spill disaster or the mining. Okay, for agriculture, for the precision agriculture, in order to estimate the actual nutrient, water and so on. Transport utilities, for you to so that we can estimate the carbon or the emission gases from the cars. Okay, and another one will be radar. Radar came from the words of the radio detection and ranging. Is an active sensor which provide their own source of electromagnetic energy. And for the active radar sensor, whether airborne or spaceborne, yeah, we have two, either satellites or you can put on the aeroplane. It emits the microwave radiation in a series of pulses from an antenna looking obliquely on the surface. Difference from the satellites will look vertical, okay, perpendicular to the surface. But for the radar, due to the concept that the system, they emits their own energy, and they will record back the reflected energy, therefore they have to look oblique on the surface, which is about 75 degrees to the surface, in order for the system to able to record back the pulses. And when the energy reaches the target, the energy will be reflected back to the sensor, and this backscatter radiation will be detected, measured and timed. So what kind of measurement is the measurement of the energy that will be reflected, and time will be time travel from the platform to the target, and from target to the platform back. So at the time required for the energy to travel to the target and return back will determine the distance and record the range and magnitude of the energy reflected. Okay, it will come out with the two dimension of image of surface will be produced, and the difference with the multispectral data, okay, the energy that we detected will be recorded in decibel unit. It's not like for the multispectral, it will form one kind of images. Radar is different. Okay. Also, because radar provide its own energy sources, images can be acquired day or night, and microwave energy able to penetrate through cloud and moss, rains, making it all-weather sensor. Okay, so what happened here? The explanation will be the microwave energy recorded by a passive sensor will be emitted from the aeroplane, okay, to the target, okay, reflected to surface, okay, or emitted. Some of it might emit surface because of the wavelength, stuff like that, okay, or transmitted from the subsurface. Because the wavelength are so long, the energy vapor is quite small. Okay, so the energy is very small, but because of the energy is very small, it requires a bigger area in order for the energy able to be reflected back. That's why radar doesn't have a high spatial resolution. It has a very low resolution images. Okay, so what happened? It goes back to the platform, and the platform will record and determine. Okay, so what kind of the radar signals that we have? We have a P band, L band, S band, C band, X band, KU band, K band, KA band. Okay, and these are the information, the destinations. Okay, usually the military are using the X band for the airborne system, for the military reconnaissance. C band for the radar sat. Okay, so C band is 3.75 to 7.5 centimeter. This is the wavelength. This is the wavelength range. Okay, and L band. Okay, so this L band and C band is what they use for the radar. So basically, the C band able to detect smaller areas, about 5 cm and above. However, for L band, it must be above 1 feet and above. Okay, so these are examples of the radar satellites. ERS-1, okay, JORS and RadarSat. Okay, and we talk about the radar. They are polarizations. So polarizations refers to the orientation of the electric field, where most radars are designed to transmit microwave radiations in the horizontal polarizations or vertical positions. So for horizontal positions, the signal will be sent like this. For the verticals, like this. Okay, and of course the receiver will also receive either horizontal or vertical, or can receive more. So what are the use of these polarizations? Basically, the idea is horizontal is quite sensitive towards the height of the tree, and the vertical is sensitive towards the dense of the trees. That's the idea. Why? Because the horizontal, you can see here. Okay, yeah, horizontal is sensitive towards the horizontal is sensitive towards this. There's a mistake just now. So horizontal sensitive towards the density of the trees, and vertical sensitive towards the height of the trees, because of the nature of the polarizing signals goes to the target. Okay, when vertical signals goes to the target, okay, it will prone to reflect on top of the forest canopy. Therefore, it can give you the characteristics of the height of the canopy. However, it will not able to estimate the density of the canopy. However, for the horizontal, it will not able to detect the height as good as the vertical, but due to the nature of it goes in the horizontal line, so what happened is it able to determine the density of the canopy better than the vertical one. Okay, so by combining those polarizations, we can have the composite data to give more and better informations on the radar reflections. So the application of radar good for the agriculture, and most of time is good for the forestry, and also some of the geology, and also the oceanography application. Okay, so that's all for the environmental observations platform. Thank you very much.